My name is Joy Mweya. I'm a product manager in Berlin, Germany. These are the project requirements. I will be using the CRISP DM process and MS Excel to train my model as I am not familiar with Python yet. Gaps in business knowledge will not be considered in the model. The goal is to predict a numeric value from a set of past numerical sensor data. This will be a supervised machine learning method using regression. I started by cleaning the data. Once ready, I generated scatter plots to have a better visual of the data relationships. I added a linear trend line to the plots in order to see the model equation and R-squared value, which tells us how much of the data is used to inform the model per feature. For temperature and exhaust vacuum, it seems to be a good fit. However, for pressure and humidity, it is overly simplistic. The arrangement of the scatter plot suggests to me that the linear model is not ideal and we may need to apply polynomial regression. This is confirmed by the next chart. Looking at the R-squared value of the polynomial models for each feature individually, the linear model is not the best fit. The example above is for temperature, which seemed like the linear model was a fit, but a non-linear one has proven better. I decided to create new features for all 4 of them with the hope of eliminating statistically insignificant features later. Before I created the new features, I analyzed the overall linear model a little further. The overall linear model 0 is of good fit with a statistical significance proven by F significance below 0.05. Some features show a negative relationship to the target and others are positive. Temperature seems to have the highest impact on energy output. All the features are statistically significant with less than alpha of 0.05. In order to start comparing with the same data, I randomized all the data and then split it 80-20 into training and test data. Model 1 uses only the training data and the 4 initial features. All features are still statistically significant with less than 0.05. The model shows a good fit and statistical significance. However, we know from the scatter plot that this linear model might fail in predicting accurately because the data as presented doesn't show a linear trend. I decided to add the 4 new features and compare model 2 performance with model 1. Using log X, I created 4 new features. Some might be eliminated in due course. Before doing an analysis of the new model 2, I selected a preferred performance metric for comparison and decision making. I chose mean absolute error as the main metric, even though I calculated the other 2 for confirmation of improvement across models. It will be less sensitive to future outliers as the data shows high variance and low bias. The p-values of exhaust vacuum and log humidity in this model 2 are above 0.05, hence not statistically significant to the model and can be omitted in the next training. The new training model 2 performs better in all metrics than training model 1, making it a more robust model. But in order to get an even better model, we will cross-validate the training data and select the best performing model from our folds. I divided my training into 5 folds for cross-validation. I calculated the average of the 5 folds cost functions. The cost function of the cross-validated model is much lower than model 3's, which had no folds. Cross-validation makes a model more robust. I then selected the best performing model of the 5 folds that would be fine-tuned to be used as a final model in the 20% test data. This was the KE3, which had the lowest validation metrics across all folds. At this point, I attempted to do a lasso regression so that I can reduce the number of features and fine-tune the overall model. It was not clear to me how to do this in Excel, so I skipped the fine-tuning and used model 4 as the final model. I proceeded to test model 4 performance as a final model with the 20% data. The final model, which is model 4, still shows overall statistical significance with test data. The R-squared of the final model on the test data is higher than that of the training data, proving that this model is a good fit. Our selected metric, MAE, for the test data is lower than the training, showing that the magnitude of error in prediction of energy output, given the 4 environmental readings for feature values, will be lower by plus or minus 3.44. In a non-academic setting, this model would require further testing and fine-tuning to make sure the deployed version is as robust as possible. I appreciate your time reviewing my presentation. Please add comments below where you feel I misrepresented information so that I can be able to learn from my mistakes. Thank you.